All right, more LaGrange multipliers. So actually let's finish the problem we were doing last time where we were trying to, let's see, let me remember. So we were trying to find the point on the plane 2x plus 3y plus z equal to 6 closest to the origin. So in this problem, we were trying to minimize the distance from our plane to our origin. So I don't really want to draw it again because my drawing's not, well, fine, I can draw it again. My drawing was not excellent last time, but it'll be still not excellent this time. Um, Here was my drawing of my X, Y, and Z axis, and then my plane looked vaguely like this, right? Where that point is X is 3, here's Y is equal to 2, and here's Z is equal to 6. And so there's some point on the plane right there that is closest to the origin like that. So the thing we're trying to minimize is our distance equal to the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared, right? Because we're calling this point x, y, z. And as I said last time, you're welcome to do this, but it's always equally good to minimize the square of the distance, or in other words, to minimize whatever is inside the radical, right? If you make all this stuff as small as possible, you're making the square root of it as small as possible, or as big as possible if you're trying to make it big. So instead, we're going to minimize d squared equal to x squared plus y squared plus z squared. And our constraint, you could leave it as is, because as long as it's everything equal to a constant, that's totally fine. But personally, I think it's always safer to be kind of systematic about it and always say it's equal to 0. So I'm going to write it as 2x plus 3y plus z minus 6 equal to 0. And then we're going to say that the thing we're trying to minimize, we typically call that f. The thing that's our constraint, we typically call that g. And then the way we find our or the way we start to try to find all our stuff is by setting the gradient of f equal to a multiple of the gradient of g. Or in other words, each partial of f equal to lambda times each corresponding partial of g. So in this case, we're going to say that we need a second piece of paper. We're going to say that we need fx equal to lambda times gx, fy equal to lambda times gy, and fz equal to lambda times gz. So in this case, let's see. Our fx is going to be 2x. Our lambda times gx is going to be lambda times 2. Our fy is going to be 2y. Lambda times gy is 3. And our fz is going to be 2z equal to lambda times gz, which is lambda times 1. Question. Okay, say that one more time. Yeah, that is a constant, exactly. Because again, the whole idea is what we're saying is these two gradients to minimize and maximize this function with this constraint have to point in the same direction, which means they're multiples of each other, and lambda is not. It's not a wavelength? No, no, definitely. Lambda is not a wavelength in this problem. And when you take 22a, lambda is also not a wavelength, and 22a lambda is an eigenvalue. So unfortunately, lambda is a popular variable name, and it gets used all the time. So yes, lambda is definitely not a wavelength. Um, so here's what I'll point out. As I said last time, there's lots of ways to do this. So I personally don't want to solve for lambda ever because I don't really need to, but one certainly could. So one way to solve this is to do what we said last time well, I should say, but I mean, when I say I don't want to solve for lambda, I don't want to find the value that lambda is actually equal to. We could, it's not really necessary though. So my go-to way of trying to deal with this is to take each of these equations and isolate lambda. So I'm going to say that lambda is equal to x, lambda is equal to 2/3 y, lambda is equal to 2z. And then pick any pair of these and set them equal to each other. So if I set these two equal to each other, I'm going to get x equal to 2/3 y. If I set these two equal to each other, I'm going to get 2/3 y equal to 2z. Since y is the common denominator, I'm going to write x and z in terms of y. Y is only the common denominator because of the two pairs I happen to pick. Right? If I had picked like this pair and this pair, I would have had a different variable that showed up in each equation. So here, I'm going to write everything in terms of y. So I have x equal to 2/3 y. That's good. I'm going to write z equal to 1/3 y. That's good. And then we use both of these along with my constraint that it's a point on the plane, right? My plane was 2x plus 3y plus z. I'm going to write equal to 6 because that feels more normal to me. And then I'm just going to plug in the value, what x is equal to, what z is equal to. So I'm going to have 2 times 2/3 y plus 3y plus 1/3 y equal to 6. To make our lives easy and multiply everything by 3, so we're going to have 4y plus 9y plus y equal to 18. So it looks like we have 14y equal to 18. So it looks like we're getting y equal to 18 over 14, which is 9 over 7. And then plug y back into these other equations to find x and z. So x is going to equal 2/3 times 9/7, which is going to be, what, 6/7? And z is going to equal 1/3 times 9/7, which is 3/7. So the closest point, how do we know it's the closest and not the furthest away? Because of the drawing, right? If you look back at your drawing over here, there isn't a furthest away point on that plane, right? You can find points that are further and further and further and further away. But that's kind of the, I would say, the drawback of LaGrange multipliers is you can't just tell you have a max or a min. You have to kind of think about why the thing you have found is either minimizing the thing you're trying to minimize or maximizing the thing you're trying to maximize. So the closest point here is going to be 6/7, comma 9/7, comma 3/7. I will also point out you could have solved for lambda first. So just to kind of show you a totally different way to do this problem, which doesn't always work. And I should say that's what this process should actually be called. The same thing never works for this process. It's always a finding your way through the systems of equations to figure out what are we going to do with these equations this time to figure out what minimizes the function or maximizes the function. But here, since each of these just has a single x, a single y, and a single z, you could also solve for x, y, and z in terms of lambda. So what I'm saying here is we could have said, question? Are they going to always be like a point of to connect to origin or close to origin? I mean, I would say if you're talking about finding things on other things that are closest to a point, yeah, but there's lots of other, like last class we did a totally different problem that was also Lagrange, where we were finding, right, we were finding the dimensions of the biggest box you could mail through the mail. So I would say no, they're not always going to be like this, but a lot of the times they are because maybe they're easy to think of. But another way to do this would have been to have taken our equations and instead of solving for lambda, solving for x, y, and z. So here, well, still it's x equal to lambda. Here it's y equal to 3/2 lambda. And here it's z equal to 1/2 lambda. Plug all of those into your constraint. So our constraint again was 2x plus 3y plus z equal to 6. So that's going to be 2 times lambda plus 3 times 3/2 lambda plus 1/2 lambda equal to 6. Add them all together. 2 plus 9/2 plus 1/2 is 9/10, which is 5. Then you get 7 lambda equal to 6. So here, not that we care a whole lot, but lambda is equal to 6 over 7. And then plugging that back in to find your x, y, and z, you're going to get x equal to 6 over 7, y equal to 3/2 times 6 over 7, which is 9 over 7, and z equal to 1/2 times 6 over 7, which is 3 over 7. The same coordinates. So sometimes you can solve for lambda and then find x, y, and z that way. And again, really the name of the game here is that there's lots of different ways to do this, usually, kind of. Really, it's like try to do your best, right? Like it's not always clear what route you're going to take to get through these Lagrange multiplier problems. So that said, let's look at some more. Let's see. Sure, here's a very standard this type of question. The temperature on the ellipsoid, so I mean, three-dimensional ellipse, x squared plus 2y squared plus 3z squared equal to 30 is given by t of x comma y comma z equal to 2x minus y minus 3z. Find the hottest and coldest points on the ellipsoid. Cool or hot. So it's the same process, right? So let's see. So we're trying to optimize our 2x minus 3, sorry, minus y. I'm just going to write minus 3z because I wrote the 3. Sorry. So that's our thing we want to maximize, minimize or maximize. And then our constraint is x squared plus 2y squared plus 3z squared minus 30 equal to 0. There's your g. And people sometimes use capital F and G, so use lowercase f and g. It doesn't really matter as long as you know what you're talking about. All right, now what? You guys do the next part. I'll give you 2 minutes to find lambda equal to things in terms of x, y, and z. Um, I'll say this is why it's a bad idea to accidentally write f in the wrong order here. Not that it's terrible, but like if I wasn't paying attention, I might have written that my gradient vector for f was 2, -3, -1, but it's not, right? It's 2, -1, -3. So this is another way you could write it. I'm instead of writing each equation out, right? Instead of writing fx equals lambda times gx and fy equals lambda times gy and fz equals lambda times gz, we can say, oh yeah, the gradient of f equals lambda times the gradient of g. Same equations. But then you kind of do want them all individually, so it's probably better to start with this. So we have 2 equal to lambda times 2x and we have -1 equal to lambda times 4y, and we have -3 equal to lambda times 6z. And this is another situation where you could kind of go either way. You could either solve each of these equations for lambda in terms of x, y, and z, or solve each of these for x, y, and z in terms of lambda. I am partial to the first thing I said. But again, really, like, you should do whatever feels more comfortable to you, as long as it's getting you to the end result. So here, I'm going to say that lambda equals 2 divided by 2x, which is 1 over x. Lambda equals -1 over 4y. And lambda equals -3 over 6z is -1 over 2z. And then, yeah.
They're all equal to lambda.
Correct. And so the thing that happens now is we select any two of them to set equal to each other. So typically I'd say this one and this one. So 1 over x equals -1 over 4y. And then you pick a different pair. So let's say we didn't, so usually I just pick these two because it seems easy. But let's pick this one and that one. So we have 1 over x equal to -1 over 2z. And then we try to essentially, well, since x is the one that's showing up twice, we want to solve each of these for y in terms of x or z in terms of x. Cross multiply, you get 4y equal to -x, you get y equal to -1/4 x. Here you get 2z equal to -x, z equal to -1/2 times x. And then you take those things and you go back to your constraint, which is x squared plus 2y squared plus 3z squared equal to 30, or -30 equal to 0, and you plug in what z and what y are equal to. So look at what this becomes. This becomes x squared plus 2 times -1/4 x squared plus 3 times -1/2 x squared equal to 30. And now it's just solving an equation. So that's usually how this goes. You use your LaGrange equations where, each partial is equal to lambda times each other partial to essentially write all of your variables in terms of one variable. And then you put those into your constraint to write that equation in terms of just one variable, which you can then solve. So let's see what we get here. So I've got x squared plus 2 times 1/16 is 1/8 x squared, and 3 times 1/4 is 3/4 x squared equal to 30. And nobody needs to add fractions. Let's just multiply both sides by 8. 8x squared plus x squared plus 8 times 3/4 is 6. X squared equals 240. So 8 plus 1 plus 6 is 15. And 240 divided by 15 is something. I think it's 18. Sure. I think it's 18. What? Let's see. Yeah. No. What is it? 16? We could actually do division, I guess. Yeah, 16. Sorry. Good to check though. Which is much nicer, right? Because a 16 is... So now be careful here. That means x is going to be what? Plus or minus 4. Again, right? We better be getting a couple different coordinates because we're trying to find the hottest point and the coldest point. So if x is 4, so here are our points. X is plus or minus 4. Y is going to be the opposite sign, so it's going to be minus plus 1/4 times 4, which is going to be 1. And z is going to be minus 1/2 times plus or minus 4, which is going to be minus plus 2. We write that to indicate that we want the signs to differ. So instead of, and also because we're lazy, that's really why we're writing, because I don't want to write both things. Because what this is really telling me is one of my points is 4, -1, -2, and the other point is -4, +1, +2. But this is expressing that. So you can get away with just writing that. Yeah. Correct. Yeah. It's just that we're literally saying the sign of 4 is opposite the sign of 1. That's why we're writing it in the opposite way. Oh, sorry. So right up here, right? If x is equal to plus or minus 4, we know that y is negative 1/4 times x. And negative 1/4 times 4 is negative 1. And if x is 4, z is negative 1/2 times 4, and negative 1/2 times 4 is negative 2. Or if x is negative 4, then y and z are positive 1, positive 2. Cool. We haven't finished the problem yet. Have we finished the problem? We have. Well, we haven't said which one is the hottest and which one is the coldest. So we actually have to plug those points back into the temperature formula to figure out which one's the hottest and which one's the coldest. So the temperature was that the temperature at the point x, y, z is equal to 2x minus y minus 3z. And if we plug in this point, so the temperature at 4 comma negative 1 comma negative 2 is going to be 2 times 4 minus negative 1 minus 3 times negative 2 is 15. And the temperature at the other point is probably going to be the opposite of that. It's going to be 2 times negative 4 minus 1 minus 3 times 2, which is negative 15. So 4, 1, negative 2 is the hottest point, and negative 4, 1, 2 is the coldest. And to some degree, pun not intended, it makes sense that the hottest point and the coldest point are kind of diametrically opposite each other on this ellipsoid. Right? If we're thinking about like kind of the temperature on the ellipsoid being continuous, right? Having to go from like, you can't just go like from immediately hot to like immediately cold right next to it. Like it's kind of gradation going down from hot to cold or from cold to hot. All right, let's see. Should we do this now? Yeah, okay. So sometimes you have a LaGrange question with two constraints, which is a little bit gnarlier. Let's take a look. So here's another example. We want to find the point, again, a point question, everyone's favorite, on the line of intersection of the two planes, y plus 2z equal to 12 and x plus y equal to 6, that is closest to the origin. You could pick another point, like to be closest to, but the origin is obviously kind of the easiest point to deal with because the distance formula is the nicest when it's the origin. But either way. Okay, I know it's really exciting, like everyone's favorite thing is Lagrange, but this one, it's kind of neat. So here's how it works for two constraints. So we're trying to, again, minimize the distance between these, minimize the distance between our point x, y, z that's on the intersection and the origin. But again, not really the distance, minimize the distance squared because we're smart. We know that's the easier way to do it. So the distance squared is just going to be, wow. Again, x squared plus y squared plus z squared. And that's our f. And then we have two constraints, right? Our constraints are both plane equations, right? Because your point has to be on both planes. So it's y plus 2z equals 12, or I would probably write it as y plus 2z minus 12 equal to 0. We're going to call that one G. And we also have x plus y minus 6 equal to 0. We're going to call that one H.
Can we just find a line of intersection?
We probably could, but it feels like a lot of work. So you're not wrong, actually. We could find the line of intersection, but if you remember us doing that, finding the line of intersection is kind of a giant pain in the ass. Like it's really probably more work than doing this, to be honest. Because then after you find the line of intersection, you'd still then have to find the point on that line that was closest to the origin. So I think this is easier in some sense, or I should say less computation intensive. So here's how it works for two. Also because we want to do it this to show this thing about how to deal with two constraints, really. So the idea here is that in this case, instead of setting the gradient of f equal to a multiple of just the gradient of one of them, you set the gradient of your thing you want to optimize equal to a multiple of the gradient of the first constraint plus a multiple of the gradient of the second constraint. Or if you want to write all the equations, the partial of f with respect to x is lambda times gx plus mu times hx. And then the same for the other ones. Partial of f with respect to y is lambda gy plus mu gy. And the partial of f with respect to z is lambda gz plus mu gz. Kind of ugly, but that's what we've got. So let's see what we've got here. We've got 2x equal to lambda times gx is, what is gx? Where's my g? Gx is 0 and hx is 1. And then this one's going to be 2y equals lambda times gy is 1. Hy is also 1. And finally, 2z is going to be lambda times gz is 2 and hz is 0. Okay, so just thinking about this logically, we should have enough information at this point. How many variables do we have? Well, technically, yes. How many variables in this system of equations? I've also, even though I've said that lambda and mu are constants or scalars, right? We're thinking of them as variables we're going to solve for. So we have 5 variables. How many equations do we have? I disagree. I disagree. I see 5. I see 1, 2, 3, 4, 5. That's good news. We want to have as many equations as unknowns because if you have equal numbers, you should be able to solve the system if it's solvable. So we're in a good shape. So now it just comes down to like, what do you do? Well, we're in kind of a fortunate spot here because we got some zeros. So let's see. We have mu equal to 2x. We have lambda plus mu equal to 2y. And we have 2 lambda equal to 2z. And honestly, this is where I don't really know exactly what we want to do. I mean, I kind of know what we want to do. We want to get rid of some of the variables. So let's see here. Well, let's see. This is lambda equal to z. Let's not be coy there. If we plug in, yeah, sure. So let's just plug in 2x for mu and z for lambda. So we can say that z plus 2x equals 2y. And then we can use that along with our other constraints, the x plus y equals 6 and y plus 2z equals 12. We should be able to make this work. Let's just say, well, again, so pick which variable. I'm seeing in these equations, y is the common thing that's showing up. So I'm going to say that y is, nope, I'm not going to say it the other way. I'm going to say that x is 6 minus y and that 2z is 12 minus y. So z is 6 minus 1 half y. And then plug those back into this equation here to get, hopefully, let's see, 6 minus 1 half y plus 2 times 6 minus y equal to 2y. And if we multiply everything by, well, let's just write it out. 6 minus 1 half y plus 12 minus 2y equals 2y. I guess I could deal with a fraction. 4y plus a half y is 4.5y or 9 halves y. And then 6 plus 12 is 18. And then multiply both sides by 2/9. So it looks like we're going to get y equal to 4. And then x is going to be 6 minus 4, which is 2. And then z is going to be 6 minus 1 half times 4, which is 6 minus 2, which is 4. So it looks like the point we're looking for is 2, 4, 4. And again, I feel like especially with these problems here, where you've got 2 constraints, it can feel real kind of like, what do you do with all these equations and all these unknowns? And honestly, the real answer would be use linear algebra. You'd make a matrix and do a whole matrix equation and solve it that way, but that's all we're doing here. So, yeah. Question?
How do we know when to use the LaGrange multiplier versus the other method?
Well, so
Like
yeah.
other than they stated.
Well, that's what I was gonna say. Is usually they tell you to. Um, well, so going back to the initial kind of statement of this question, we could have right. This didn't say use Lagrange. We could have done it the other way. We could have said, all right, I'm going to first find the line of intersection, which is not a small feat. Although it's probably not as terrible here because we don't have as many variables going on here. And then you're going to like you find it's been like how do you find the line of intersection again? I've kind of forgotten how you find the because I'm trying to think about where lines intersect, not where planes intersect. Ugh. Do we want to do it the other way? I kind of wanted to. Okay. I remember how to do it. So the way you find the line of intersection is by taking the normal vectors and their gradient, sorry, their cross product to find the vector that's the line of the direction of the line of intersection at one point. So actually finding the line of intersection is not that bad. And then once you found the line, you would then say, okay, point on the line, trying to minimize distance between that point and this other point, and then you would have essentially a function of two variables once you eliminated one of them. So the answer is good question. Because really, there isn't one reason to do it one way or the other than it ends up sucking a lot more doing it one way than the other. But that's a matter of opinion, really. Fortunately, most of the time on exams, they usually tell you if they want you to use Lagrange. Yeah, that's.
You don't think he'll do that?
I don't think he's gonna say. I don't think he's gonna say like find the closest point or maximize this thing and not and not say Lagrange and expect you to have used Lagrange.
So if it doesn't say LaGrange, probably use the other one.
I would think so. Okay, let's look at one more. Yeah, one more. It's kind of weird. Sure, we can look at this one. Yeah. So I forgot what number I'm on. I think it's number 4. So we want to use Lagrange multipliers, or just Lagrange, we know what we mean, to find the extreme values of f of xy equal to 3x squared plus y on x squared plus y squared equal to 1. So, do I want to say that yet? Not really. We'll talk more about this in a second here. Well, let's just go through the process and see what we get. So, let's see. So setting our let's see. So I'll point out here, it's perfectly fine to just call this G and not bring the 1 over to the other side. Because it doesn't matter which side of the equation your constants are on if you're taking partial derivatives. So here, our gradient of f equal to lambda times our gradient of g. So let's see, we're going to get fx, which is 6x, equal to lambda times gx, which is 2x. Don't really need to write all that, but okay, I did. And then fy is equal to 1, and that's going to equal lambda times gy, which is lambda times 2y. So my equations written terribly are 6x equal to lambda times 2x and 1 equal to lambda times 2y. Now this is where things get kind of interesting. Yeah. Uh-huh. I wrote fx equal to 6x equal to, and then I wrote it's equal to lambda times the gradient of g, which is 2x. And then I wrote lambda times gx. So I was trying to like show everything and kind of got a little bit messy there. But so I've got my fx equal to my lambda times gx and my fy equal to my lambda times gy. Now, here, this is an example where you actually have to be a little bit more extra careful than you might usually have to be. So you might, well, let me point out. What does lambda have to be here? Kind of. Like if you look at this equation, lambda times 2x equals 6x, gotta be 3. And then if lambda is 3, you can solve for y. So if you're not careful, you might convince yourself that lambda must be 3, and then 3 times 2y equals 1, so y has to be 1/6. And then if y is 1/6, we can find the value of x by saying, well, x squared plus 1/6 squared equals 1. So x is going to be plus or minus the square root of 1 minus 1 over 36 is 35 over 36. And that is one of the points we have to consider, where x is plus or minus that and y is that. But it's not the only option. So when you're solving these equations, you have to be extra general. You can't divide both sides by a variable, which is what I was actually kind of doing without saying I was doing it, right? When I said here that lambda is equal to 3, I was kind of pretending like I divided both sides by 2x and got lambda equal to 3. But we should be more careful. We should say, hey, we're going to bring everything to one side and say that lambda times 2x minus 6x is equal to 0, and then factor out a 2x and say that 0 is equal to 2x times lambda minus 3. So option 1, lambda is equal to 3. And then you get exactly what we said we got. Option 2, well, another solution to this equation is x equal to 0. And then if x is equal to 0, we get y equal to plus or minus 1. So we have 4 points in contention that are going to be the extreme values of this function. We have 0, 1, 0, -1, positive root 35 over 36, comma 1/6, and negative root 35 over 36, comma 1/6. And then to figure out which one are the extremes, you actually have to plug them into the original function. So let's see here. So f of 0, 1 is going to be 3 times 0 squared plus 1. F of 0, -1 is going to be 3 times 0 squared minus 1. Those are the easy ones. These are the harder ones. F of root 35 over 36, comma 1/6 is going to be, okay, 3 times that number squared is just that number, 35 over 36, plus 1/6. Yeesh. Let's see. This is 35 over 12 plus 2 over 12, which is 37 over 12, slightly bigger than 3. And the other one, if I plug in, I think it's the same value. If I plug in negative square root of 35 over 36, right? Because I'm going to get 3 times still 35 over 36 plus 1/6, which is still 37 over 12. So here's our minimum. Here's our 2 maximums. Interesting, kind of. Here's what this means graphically. In fact, I think this is a good moment to kind of see this up. So what we're really doing is we're saying this. We're looking at, sorry, let me pull this up here. Because I do think this actually kind of helps make things make a bit more sense. Yeah. So yes, you can have multiple maximum subject to a constraint on the kind of like how the sine function has an infinite number of absolute maxima. So here we go. Let's first graph the thing we were trying to maximize or minimize, which was z equal to 3x squared plus y. Okay, looks kind of funky. All right. And then our constraint was the cylinder x squared plus y squared equal to 1. Why are you giving me grief? Okay, there we go. So look, right there is a maximum value on that that's still on the cylinder. And wow, I got this nice rotation going. There's a minimum or a potential minimum. And then coming around again a little bit faster. Okay, please speed it up. Oh, geez.
Why
So
is
how,
the cylinder not filled?
well, so right, it's not a solid, right? It's a surface.
It's-
But let's actually plot the points we talked about. So the points were 0, 1, 1 and 0, 1, -1. Let's see, where are those points? So look, oh yeah, look. Oops, except 0, -1, -1. Apologies. So look, there's that 0, 1, 1 right there. And over here, you can see, you can see, right? You can see the point right there, maybe. Can I see the point right there? Why would you make it purple? God, sorry. Let's make that point a different color so we can actually kind of see where that, there, now you can kind of see it. So you can see that point right there. That's your absolute minimum of this surface subject to the constraint that you're on the cylinder. And then our two maxima are there and on the other side. And if we plot them here, which is a little bit grosser to plug in, it's the square root of 35 over 36. And then the y value was 1/6. And then the z value was 37 over 12. Oops, come on. And I guess it's on the other side. This couldn't be on the side I picked. There it is right there. So kind of cool, right? Like this actually works. Like we found the highest point on this red surface that was also on the cylinder, and the lowest point that was on this red surface and also on the cylinder. So we maximized the values of that red surface subject to the constraint that we were on the cylinder. It's neat. All right, that's all I got. I know it's 3:54. We can end it a few minutes early.
You find the points
Uh-huh.
where like we had 0, 1.
Right.
The square root and then a 1/6.
Right.
Where
So
do you put those? I missed that.
well, so I say, so to answer the question, right? The answer to this question is, well, the question was, use LaGrange to find the extreme values of this function. So the extreme values are -1 is the lowest possible value, and positive 37 over 12 is the highest possible value
Okay.
at
So you
these
just
points.
you just take those critical points, plug them back in, and then whatever one's
Right.
high, whatever one's low.
Right. It's kind of like how we found like how we maximize minimize functions on a closed boundary. Right. You found your critical points and then all your like corners and side points. And then once you have all your candidates, you plug them all into the original function to see what's the biggest and what's the smallest. Yeah. Cool. All right.
You're gonna cover more on Friday, or are we gonna do a review?
I don't know what we're gonna do on Friday. I guess we could I mean, I feel like we've kind of reached the end of the material, so I guess some sort of review would probably make sense. I just had to think about what. I suppose I should say come with questions.
Okay.
I'm happy to go over anything, but I'll try to come with a broad overview of what you might want to be thinking about for your final.
Does this class cover what we learned in lecture today?